Thank you very much for the introduction, and I would like also to thank for the possibility to present my talk. And I would like to share with you the results of our studies on the quantum devices, and present the quantum protocols for these studies. So the outline of my presentation is the following. So first of all, I would like to share with you and to say a few words about quantum graph states, their structure. Then we discuss about geometric properties of quantum graph states, and we found relation of these properties with properties of graph. Then we will discuss the geometric measure of entanglement of quantum graph states and its relation with degree of vertex in a graph. And the final stage, it will be the quantum algorithm for studies of graph properties and our results obtained on IBM's quantum devices. So let us start. Let us consider a physical model, a system described by Hamiltonian. So we have the following Hamiltonian introduced in this slide. And if we consider a state, a quantum state, corresponding to this system, the evolutionary state. So if we consider some initial state and then consider some operator, the operator of evolution corresponding to this Hamiltonian, we obtain a quantum state which has a structure of graph. So this quantum state can be mapped to some graph. In this slide, you can see how it can be. So we can consider some graph, and the graph consists of vertices and edges linked these vertices, and the state corresponding to this graph is constructed with the help of action of two-qubit operator or two-spin operator in this case. So we have different terms corresponding to existence or absent to existence of interaction between spins. And here we have links between vertices. So each link corresponds to the interaction in spin model. So for each quantum state, we can map a graph. Of course, there are different possibilities to construct quantum graph states, and at the end of my talk, I will discuss the possibility to create multi-qubit graph states with the help of another two-qubit gates. But I would like to note here that we have a state of a quantum system. We have a state of a spin system. So we have a real physical system. And we can study the system with the help of notions and also results in graph theory, because we have this mapping. And vice versa, we can study graphs with the help of results and on the basis of results of quantum calculations. So how to do this? I would like to show you on this slide that in the case of this model, as a model, if we calculate the mean value of squared Hamiltonian, we obtain that this mean value, in the case when all these interactions are the same, so all these J constants are the same, this mean value is related with the total number of edges in the graph. So we can find the total number of edges in a graph corresponding to some Eisen model, to some physical system, with the help of calculations of this mean value. On this slide, I would like to show that if we calculate the mean value of Hamiltonian this third power, we obtain that this mean value is related with the total number of triangles in a graph. So we also have the relation of quantum property of quantum value, value from quantum mechanics with properties in a graph, because we have this mapping. And in this case, if we calculate this mean value, we obtain here the total number of edges, K2. We obtain here also the total number of squares in a graph. So if we can calculate these mean values on a quantum device, we can study these properties of graphs, namely the total number of edges, the squares in graph, and also triangles in graphs with the help of quantum calculations. I would like also to note that in a recent paper, it was shown that the geometric properties of quantum states are related with these mean values of Hamiltonian. Hamiltonian in the third power, fourth power, and the squared Hamiltonian. So let us discuss these geometric properties of quantum states. Let us consider these properties. So let us discuss the velocity, curvature, and torsion quantum states in evolution. So it is known that the velocity of quantum evolution is defined with this expression. So we have here the mean value of squared Hamiltonian. And also we can introduce and we can also define the geodesic line as in a classical case and as in a classical mechanics. Similarly, in a quantum mechanics, we can define this line, and it was done in this paper, the paper published by Professor Tkachuk and Dr. Laba. And the expression for this is the following. Also, if we know the geodesic, we can introduce the radius of curvature. And it's very interesting that the radius is related with these mean values. Also, the details you can find in this paper. And similarly, and as in a classical case, we can also say about torsion in a quantum of a quantum evolution. So the torsion is defined with also these mean values of Hamiltonian in different powers. So the details can be found in this paper. So it was explained in details how to introduce all these notions. But I would like to focus your attention on that thing that these mean values in the case of quantum graph states are related with properties of quantum graphs. So with the help of studies of geometric properties of quantum graph states in evolution, we can detect the number of triangles, the number of squares, the number of edges in a graph. So in our case, in the case of quantum graph states, we have that the velocity of quantum evolution is related with the total number of edges. Also, the curvature is related with the total number of edges and total number of squares in a graph, and torsion is related with total number of triangles and also the total number of edges in a graph. So we have obtained these relations. And how to study these properties on a quantum device. So how to detect these properties on a quantum device? For this purpose, we have to find these mean values. So let us consider, first of all, very simple case. So let us consider, first of all, the case when we have the Eisen model and we have only 3 spins, they interact with each other. So we have interaction between 0 spin with 1, and then we have the interaction between 1 spin and the first spin and the second spin. So we have a structure of graph corresponding to this state, this quantum state which corresponds to this model. So we choose the initial state to be 0, 0, 0 because it is very convenient, and the quantum device, we have prepared this state. And then we have the operator of evolution with corresponding to this model. And this quantum graph state corresponds to a chain. So if I consider a graph, I have only 3 nodes and they link which is each other, and we have a chain. So how to study the mean values of Hamiltonian in this case? We know that to calculate the squared fluctuation of energy, we can use different different ways. And the first step is to consider the mean value of the operator of evolution and consider small times. So if we have small times, we have here the term which is related with this squared fluctuation of energy. And if we can detect this mean value, we can detect this coefficient, this, and also this term. To do this, the quantum protocol for studies of the mean value of operator of evolution is presented in this slide. So we have 3-qubit protocol. We have qubit 0, qubit 1, and qubit 2, which corresponds to spin 0, 1, and 2. And we have interaction between spin 0 and spin 1. And in this case, we have interaction between qubit and qubit 1. We have here 2 qubit gates. So this part of quantum protocol corresponds to this exponent in a power sigma x0, sigma x1. So we have interaction between the spins. And this operator can be realized with the help of controlled node operator, Adamar gate, phase shift gate, also Adamar gate, and controlled node operator. Also, we have interaction between spin 1 and spin 2. So also we have here the same part of protocol, very similar, the same as we have here, but we have relation of qubit 1 and qubit 2. And after that, we have measure the states of all qubits in standard basis to define this mean value and the results of measurements. So we realized this protocol in a quantum device, and it was IBM Q Manila. It was a 5-qubit quantum device, IBM's. We changed this parameter phi in this gate to detect the dependence of this mean value on time and obtain very nice result, because the process corresponds to calculations on a quantum device, and the line, red line, corresponds to analytical calculation. So we have very good agreement. It is because the quantum protocol is not complicated, so we have not many gates, and we have small gate errors. But to find this mean value, to find the quadratic fluctuation of this energy, we have to consider small times. Therefore, we have to consider small parameter phi. And we calculated also this dependence for small times. In this case, we have not such a good agreement. But on the basis of this result, we obtain the mean value, which is very for this mean value, which is close to the analytical results. Another way to find this h squared, the mean value of the Hamiltonian squared, is to calculate this mean value in the case of our spin model, in the case of our model described by Eisen model, and find the expression for this h squared. In the expression, we have that the Hamiltonian, the squared Hamiltonian, is determined by this term. So we have sigma x0 multiplied by sigma x2. So the mean value of these operators can be easily determined on the basis of results of on the basis of the results of quantum measurement, which we do in a quantum device, because we measure here projection on the basis states 0 or 1. These states are eigenstates of operator sigma z operator. But we can easily find this mean value if we know that the sigma x operator can be represented by sigma z operator. But we have here this multipliers, we have here this exponents, we have here the rotational gates. Also, this one gate, this one operator can be represented by also sigma z operator, but we have here this exponents. So this mean value can be represented by this one, but in another state. So here we have 0, 0, 0 state, but here we have some another state which can be obtained after the action of rotational operators on the 0, 0 state. So this things corresponds to the probabilities to obtain the reduction of a quantum state to 0, 0 state, 1, 0 state, 0, 1, or 1, 1 state. So knowing these probabilities of quantum measurement, we can calculate this mean value. And we do this, we have done this on the quantum device, also IBM's quantum device, 5-qubit IBM's quantum device. And protocol for this studies is very, very, very simple, because we have only 2 qubits. We have to rotate the states, and then we have to measure. So in comparison to this one, more simple case for the calculation, and we obtain this result. So on the basis of the results of quantum calculations, we obtained 1.98. Theoretical results gives us here the multiplier 2. So it's close to the theoretical result. And similarly, we can calculate the mean value of h to the third power and h to the fourth power. So we have also these results. And on the basis of these calculations, we can detect the number of triangles, squares, and edges in a graph. Of course, if you have such a simple graph, it's very easy to say that we have no triangles, we have no squares, and the number of edges too. But this example is to test this algorithm on the real quantum devices. We also considered more complicated graph state or more complicated spin model. So this spin model corresponds to a graph with the structure of triangle. So we have also 3 spins or 3 qubits, and they interact with each other with the following way. So we have 3 terms corresponding to the 3 edges, and we have the following quantum graph state. The quantum protocol for studies of the mean value of the operator of evolution in this case is the following. So here we have more complicated protocol, because we have 3 multipliers, and we have here also 3 parts of protocol. And after that, we have quantum measurement. On the basis of quantum calculations, on the basis of quantum programming, we detect this dependence of the mean value of the operator evolution on a quantum device. So you also have a good agreement with the analytical calculations, and also for small parameter phi or for small times, we also obtain results which give us the mean value of this mean value. Also, of course, we test our algorithm, we test this relation. For more complicated graph, it is square graph, because we would like to find the number of squares. In this case, this number is equal to 1. So we have the following Eisen model, we have the following quantum graph state, we have the following protocol, so very similar to the previous cases, and we have also nice results and good agreements. Their work was done in collaboration with Hanna Laba and Professor Tkachuk, and all these results I presented in the previous slide were published in Physics Letters A. So you can find more details of these calculations in this paper. And I would like to move forward. So let us discuss another properties of graphs which we can detect on a quantum device. So another property of graph, maybe I will show once more again the structure of graph. It is the vertex, the degree of a vertex. So for each vertex, we have number of links which connect this vertex with the graph. For instance, for this vertex, we have the vertex degree of this vertex is 1, because we have only one link. In the case of this vertex, we have 3 links. So the degree of this vertex is 3, so on. So in the case of complicated graphs, it is not so easy to calculate this characteristic, this property. So we have to check if this vertex is linked or not with other vertices. And on a quantum device, we can do this in a simple way, because we obtained relation of the geometric measure of entailment on the with vertex degree. So let us consider this measure of entailment, the geometric measure of entailment, which is defined as minimal squared Fubini study distance between some state, which we would like to find to consider, and a set of non-entailment states. Was introduced in this paper, this definition. And in this paper, it was shown that we can find the geometric measure of entailment of a spin or a qubit with other qubits by calculating the mean value of spin. So we have this expression. And we considered different graph states. I promised to show another structure, graph states constructed in a different way, another way. So it is known in the literature that we can construct a quantum graph state by acting of 2-qubit gate. For instance, it can be a controlled Z gate. In more general case, it can be controlled phase shift gate. So we have this 2-qubit gate, controlled phase shift gate, and we have this some initial state. We considered very general case of this initial state. And with this action, we construct entailment state, which can be mapped to a graph. So we also have a link between vertices or nodes if this operator acts on the state. And the geometric measure of entailment of a qubit with other qubits in this graph state is related with this parameter, and this parameter m with index L is a degree of vertex with index L in one graph. And for more details, you can also find and read this paper. And we also calculated, in this paper you can find results of quantum calculations, of course, and here I would like to show you another graph states and the results of calculations of the geometric measure of attainment on a quantum device for quantum graph states with a similar structure I considered in the first slide. So we have Eisen model, and we have the initial state 0, 0, 0, 0. And if I have a 5-qubit quantum device, the quantum graph, the graph which can be studied on this device is graph which consists of 5 vertices. And for instance, it can be a complete graph. So each vertex is linked with other. And to study this graph and to prepare this operator, we have to use not simple protocol. We have a lot of gates here, and this U gate is composed with Adamar gate, phase shift gate, and also Adamar gate. So we have also controlled NOT gates. We have here very simple case when we have action of this gate on this initial state 0, 0. So 0, 0 is prepared on the initial state and stage, and then we have the action of this operator. We would like to calculate the mean value of spin because of this relation. We would like to find this attainment, so we have to calculate this mean value of spin. And to do this, we also rewrite our sigma x Pauli matrices by sigma z operator. So we have to rotate our state, and these values can be found from the histogram, which corresponds to the results of measurements of quantum measurements. So to find the mean value of sigma x, sigma y operator, we have to find these things, and the mean value of sigma z operator can be easily found on the basis of the results of quantum measurement. And we obtained the results of measurement on the basis of the results of quantum measurements and on the basis of the results of quantum calculations, we obtained this relation of attainment on the parameter phi. So we have also the red line corresponds to analytical results, and the crosses corresponds to results of quantum calculations. We have also very nice mapping. So on the basis of studies on attainment of quantum of a qubit with other qubits, we can detect another property of graph. It is the degree of vertex. Also, more details can be found in this paper. And I would like to conclude maybe before the questions. I would like to conclude that the properties of quantum states, they are geometric properties of quantum states, attainment with properties of graphs. So we can study complicated graphs with development, of course, with development of multi-qubit quantum computers. We can study the properties of graphs with the help of quantum programming. And we hope that the proposed algorithms will open the possibility to obtain a quantum supremacy, because to calculate the number of triangles, to calculate the number of squares, and to calculate the number of edges, it is not a simple task in graph theory. So, but in this case, we have to find these mean values of the Hamiltonian is the second power, Hamiltonian is the third power, fourth power, with the help of quantum calculations, and we obtain this value directly with the help of quantum programming. So thank you very much for your attention. Thank you.
Well, thank you for your talk, and talk is now open for discussion. Are there questions? Yeah,
Yeah,
Mr. Pomorski.
yeah, so actually I have some comments in relation, because basically what you do is you do spin-based quantum computation, right? That's what you do. So actually I just wonder how your system that is Ising model can be converted to interacting single electron devices. I mean, semiconductor single electron devices. So if you have a double quantum dot system on the left and on the right, the presence of electrons in one dot is like spin up, and then it could be in second lower dot spin down. So actually there are some formal analogies. So I'm just thinking how much your results or your methodology could be retranslated to a single electron devices. Do you have any possible thoughts on that direction?
Yes, thank you. Thank you for your question. So maybe I will my full screen regime. It's very nice. So very nice question. So why do we choose Ising model? Why do we choose not Heisenberg model or other systems? Because we can easily create these operators of evolution on a quantum device. So this like this exponent with this sigma xx or this sigma z corresponding to the Ising model this gate is known as ZZ gate of XX gate, and in our case we have very simple protocol for creation between. So I would like to also to note that these gates commute with each other, so we have no problem with creating very complicated quantum graph states. Therefore, we choose this Ising model. Of course, it is interesting to consider other physical systems and to consider more knowing this information, maybe for improvement of algorithms of quantum studies. So thank you for the question. The reason for choosing this Ising model was this. So we can easily create this operator of evolution on a quantum device.